Okay, in that case, I'll start. Okay. So, good evening, everyone. Welcome to the final talk of this foundation course on group theory. So, my name is Snehinh Sen and I'm a student of B.Math third year. I'll be taking the talk, and the topic for today's talk is structure theory of groups. So, I'm assuming that you're familiar with the basics of groups, like the definitions, like subgroups, quotients, then you have quotients, and then center, some certain examples, then direct products, conjugacy classes, etc. I am assuming that every attendee is familiar with those topics. Is it fine?
Yes.
Okay.
Yeah,
In that case, let me just give you a brief overview of what we'll be covering today. So we'll have a brief recap of conjugacy and class equations, specifically to prove a result which we'll need. And then I'll state the correspondence theorem because I'm not very sure whether it has been covered or not. It is one of the most remarkable facts about basic group theory. And then I'll introduce the process of induction on groups, mainly abelian groups, and show a few applications specifically to P groups, a special type of group. And I'll state the fundamental theorem of finite abelian group as well as the basic theory for finitely generated abelian groups. We won't get we won't be dealing with it too much. Like we won't get too deep into it. We'll just look at the results and try to understand what they mean. Then I'll cover a few structural results like Cauchy's theorem. I think Shahib has already covered Cauchy's theorem in the last class. I'll state it as well as a much more stronger theorem called Celo's theorem. And also, like for Celo's theorem, there is also a nice equivalent abelian form which will give you the fundamental theorem of finite abelian groups. I'll state that as well, and I'll talk a bit about commutators, abelianization, then various series of subgroups like subnormal series and composition series, and that will lead us to analyzing what is called simple groups and the Jordan-Holder theorem. And we'll end the class with a brief homological consideration, in the sense we'll define what exact sequences of groups are and give a homological form of what semi-direct products are. You might have heard of this term semi-direct product. And there is actually a very concrete definition of the same. You can find it in many references like Hamilton Fort or Freely for that matter. But we'll look at just the motivation, or as to why is it kind of dual, or not exactly opposite. In mathematics, there is a notion of duality. So we'll look at why it's a dual of direct products in that sense, and how is it related to direct products. So I'll start with this talk. So as for conjugacy, you know what conjugate elements are and essentially what conjugacy is. So we say A is a conjugate of B if there is a G belonging to G. Throughout this talk, I'll assume that if I mention G is a finite group, unless mentioned otherwise, only one section we'll look at finitely generated, which is a
excuse me.
generalization of this. Yeah.
Are you
Sure.
sharing your screen, because we can't see anything?
Oh, I'm so sorry. I think that was an error. Yeah, I was sharing my screen. Okay. Is it visible now?
Yeah, it's visible now.
Yes.
Okay, so I just read this thing else. And then for conjugacy, I'm sure that throughout this talk, I'll assume that whenever I'm talking about a G or a group, it is finite. Not necessarily abelian, but it's finite. G is finite unless mentioned otherwise. For example, some results which we'll prove will be valid for infinite groups as well. But you'll see, like for P groups, the neat characterization or some results, neat results are actually rely on the fact that G is finite. So even if you don't assume that, I'll assume at least that G is a group. So I'll take that for granted, and I'll say that A is a conjugate of B if there is a G belonging to the group G such that G inverse A G is equal to B. This is sometimes denoted by A par G or AG notations, but yeah. And it's a very easy exercise that this is an equivalence relation. And effectively, not just an equivalence relation, kind of arbitrary equivalence relation. The equivalence relation actually links elements which are very much similar to each other. Like they have the same order, they generate similar subgroups, and so on. Like they are essentially the same element up to some shifting, you might call it. So because it's an equivalence relation, you have done some basic set theory. So every equivalence relation gives rise to a partition, which is the set of equivalence classes, and these equivalence classes are called the conjugacy classes. So the classes, equivalence classes, which are denoted by G or like a quotient symbol, this is basically the conjugacy classes. So you have done some group actions as well in the last one. So you might have seen this fact that if this is the conjugacy class of G,
కొంచెం రావడానికి
and
లొకేషన్
this is the centralizer of G. Have you seen what a centralizer is?
Yes.
Okay. Then have you seen this result? Product of these two sizes is the size of G.
Yeah, it's the orbit stabilizer theorem.
Yeah, exactly. Just a direct application. This is a group action. Conjugacy is also a group action, and it's very easy. It's a group action, and well, you get the orbit stabilizer theorem. Over here, the way I have written it, it is a right action. You can give the other way as well, other way around, and well, those are just stuff, I guess. Okay, so now that this thing is familiar to you all, I think you have also seen the class equation, and this, as a corollary, you get that the size of the conjugacy class divides the size of G. And the class equation is basically, you write G, because it's a partition, the set of conjugacy classes is a partition of G, you can write it as the sum of the sizes of the conjugacy classes, right? Where n1 is less than equal to nk, like it's an increasing sequence. So in that case, basically, these are the sizes of the distinct conjugacy classes, and from the above fact, you have that ni divides the size of G. And how many ones are there? Number of ones in the number of ni equal to 1. Like how many elements have a singleton conjugacy class? See, an element has to be there in its conjugacy class because it's 1G1 inverse. But generally, it has more than that element, in the sense there are other elements as well in a conjugacy class. But which elements or what kind of elements have only one element in the conjugacy class? That is, when is this true? So what's the answer? Anyone? So what is the definition of the conjugacy class? It's basically elements, like if I use this definition, it is basically set of all such elements, right? And I'm saying this is equal to this set. So what is it happening exactly? Anyone?
So G is in the center of G.
Exactly. So you will get AG A inverse is equal to G for all A belonging to G, and that would imply G belongs to the center of G. Perfect. So the number of ones is equal to the size of the center. So this is a very important equation, and you'll see its application everywhere. And I'll give a very brief application pretty soon, and I'll write the result for you to think about it for a bit. It's basically, if I give you a group of size p square, where p is a prime, then G is abelian, and in fact something stronger, in a sense, like something much general. If G, the size of G is a power of p, then the center of G is not, see, 1 is always in the center, the identity, but it is strictly larger than the center. That is, the center of G is not equal to the trivial subgroup. So we'll look at this fact in a short while. Okay. So I guess this is more or less whatever I wanted to recap about the conjugacy classes. Now, also there is one more concept called the conjugacy of subgroups. I'm sure you have seen this as well. If H is a subgroup of G and G is an element of G, then I'll define, or perhaps I'll just avoid the notation. I'll consider this thing, which is basically the set of all elements of this form, where H belongs to H. G is fixed, by the way, over here. Then you can show that this is a subgroup of G, and it's not very hard to see that it is a subgroup. And the interesting fact is if G inverse is equal to H for all G belonging to G, what are such groups called? I'm sure you have seen this.
Normal.
Exactly. So over there we had the element is in the center, and over here we'll have if a subgroup has, see again this is an equivalence relation. So if you look at the conjugacy class for this subgroup, if it's a singleton, see H is there, and if it only H is there, then it's normal. So that's why normal subgroups also come up naturally using conjugacy and these equivalence class concepts. It is kind of like the center of the set of subgroups in a sense. Okay, so that implies H is normal in G. Perfect. So if these things are clear, I'll head to what is called the correspondence theorem. So this has many forms, and one form is there in the group action format, and that is very important. But the one I'll be interested in is simply the subgroup nature of quotients, for that matter. You can generalize this to, in general, like group homomorphisms. I'll just state it for quotients. So let G be a group again, and let H be normal in G. So I am interested to know what are the subgroups of G mod H. So do you know a characterization? Have you covered this part where you can sort of give me a description of all the subgroups, or give me a bijection between something which is easier to study and this set of subgroups?
This is the isomorphism theorem.
Exactly, it is kind of the isomorphism theorem, but something a corollary. Like if you know the isomorphism theorem, this kind of follows from the isomorphism theorem. Not exactly a corollary, but related result. So my claim is these two sets are in an these two sets are naturally bijective. So what are the sets? Subgroups of G mod H, the set which I am interested in, and the subgroups of G containing H. That is all. If I want to describe this thing, it is basically all N, which is first of all a subgroup of G, and also H is a subgroup of N. If H is a subset of N, it has to be a subgroup, and because N is a group once again. So this is the correspondence I'm interested in, and this is naturally bijective in the sense the norm first case, which is you have seen this thing. So there is a natural surjective map where G equals to G bar, right? Or the left coset GH. Over here, the left coset is the right coset. You have seen this map. This is a natural surjective homomorphism of groups. Just using this, you can talk about this correspondence. So have you seen this result? Or should I discuss it more about it?
It wasn't done explicitly.
Okay, I'll discuss it. So the main idea is, if you know quotients, the idea should be clear. If this is your G and this is your H, so what exactly is a quotient? You're basically shrinking this H to a 1 inside G, right? In this G bar or G mod H group, you're shrinking this H to a 1, or doing away with the information present in H. So the whole group is also proportionally shrinking, right? So any subgroup of G mod H must contain 1. So if you pull this back to G, you'll have to kind of contain the whole of H, and you also get a subgroup. That's not hard to see. You can verify it using this map. And I'm sure you have seen this. Like if phi from say G1 to G2. If H is less than equal to G1, then phi H is less than equal to G2, and likewise phi inverse H prime, where H prime is less than equal to G2, then phi inverse of H prime is less than equal to G1. You've seen this fact. I'm sure about it. So otherwise, like, this is an easy exercise. And using that, think of this. So basically, if you have a subgroup over here and pull it back using this map, you'll get something which is a subgroup, call this some K, which contains H. And in fact, take a subgroup K and then you can just again push it forward by this projection or quotient. So basically, this is the idea, and you will get there is an immediate correspondence and a bijection like this. In fact, it's something called an isotone connection. So, like if over here in a set, like there is a containment, the containment is preserved, and so on. Like those are just simple facts, simple to visualize. But just think of it using this diagram. So, is this clear? Because we'll need this idea later on.
Yeah.
Perfect. So, if it is clear, perhaps a question to wonder about is, suppose, say, okay, one more thing is, so this K, what is its image precisely? If I want to talk about it as a group, can you describe me the image of this K? Like, what I'm asking is basically, suppose there is this G, and as I'm saying, an intermediate subgroup H, a subgroup which contains H. This is being mapped to a subgroup of G mod H, right? That's what we were talking about. So, what is this image precisely?
K mod H.
Perfect. It is K mod H. So if you this is our image, this K mod H, that is what we are interested in, and you can also pull it back and do some tricks. My question is, when does this hold? Or when does this hold? Like, not, my question is not whether this holds, like, when does this hold? So just think about this. But I'll state an answer later on. But it's a good habit to just try to answer it yourself. And it basically, if you know a bit about it, the third isomorphism theorem is closely associated to this result. It's sometimes also called the second. Basically, the quotients part, that is, if this is true, then you can talk about this thing. Then this is isomorphic to this. If K is also normal, like if both of these hold, like that's true. But try to think of the opposite question as to when can you talk of these things in the sense, when is this normal and this? Okay, that's my question. Okay, so we're now headed towards induction of groups, mainly abelian. So you know what induction is, like the strong form, weak form, and also the well-ordering form of induction. Are you familiar with these forms of induction, everybody?
Yeah.
Okay. In that case, perfect. In that case, you might have realized that groups have an associated order, right? The size of the group or order of the group. So it's a natural guess that you can or you should be able to apply induction on groups. In a sense, like suppose a result is true for this, then it is also true for this. Like you can develop some methods to prove this. But the first, after the first class in group theory, you'll realize that that's not a very feasible idea. The main reason is sometimes the n plus 1 is much simpler to study or deal with than n, and sometimes the n plus 1 has no relation with n as such. It can be very, very different in a sense. For example, in the first class, you might have proved this fact after doing Lagrange theorem, that is, if P is a prime and size of your order of G is P, then G cyclic. Have you seen this?
Yes.
Yes.
Yeah.
Yep. Perfect. So if you have seen this fact, it's obvious that any group whose order is prime is first of all unique and in a sense like up to isomorphism, and it is very simple to study. Cyclic groups are the easiest groups to study. So on the other hand, like your p minus one might be very weird or very very wild. Like first of all, it's abelian. So a group of size p minus one might not be abelian. For example, S3. Your group of size 7 is just Z mod 7Z or the cyclic group of order 7. But there is a non-abelian group S3 before Z mod 7Z size. So to apply induction, it's like there is no need to do it this way. Likewise, if you assume this, for example, then how can you actually show it for say Q8 or D8, like whatever groups you have covered? I'm not sure which one you have. Q8 is the quaternion group of 8 elements, and this is the dihedral group of 8 elements. Have you seen these two groups?
We have seen the dihedral group.
Okay, the quaternion is a very interesting group. It's kind of like the main idea was to generalize complex numbers in a sense, physical sense. So it is the set of elements of this form. The identity is 1 basically, and minus 1 is just a normal minus 1. And I is like the complex I. Okay. So it's basically I power 4 is equal to 1, I square equal to minus 1, and so on. Likewise, J is also like the complex I in a sense. And likewise K. And how do you link these quantities? Do you remember the vector, what was it called? Cross product? In physics? Yeah.
Yes.
So there was this thing, right?
Yeah.
Remember this? And that is how we link it over here. So you link Ij is equal to K, Jk is equal to I, Kj is equal to, sorry, Ki is equal to J. And in a very similar spirit, what should Ji be? If you think of it as cross products?
Minus K.
Exactly, it's minus K and so on. And you can also prove it from this. Basically, it's enough to say that I power 4, J power 4, K power 4, I square, J square, K square is equal to minus 1, and Ijk is equal to 1. You can verify that it's enough to say that. Wait a second. Yeah, what did I say right now? Ijk equal to minus 1. Sorry, not minus 1. Yeah, my mistake. So this is what you have to. It's equivalent in a sense. So just think about it. Think about these results, and you'll realize that this is a group, and it's non-abelian, of course, because Ij is not equal to Ji. Well, so this is also a group, and this is also not isomorphic to D8 because there, in D8, how many order 4 elements are there? D8 has basically like there is this one R square, and R cube. Then there is this S, SR square, SR cube. These are reflections and involutions, right? Or transpositions, like order is 2. This has order 1, this has order 2. So there are 2 order 4 elements. You have seen this representation of D8, right, by the way? Using S and
Yeah.
R?
Yes.
Yeah. Then these 2 are the only order 4 elements. And how many order 4 elements were there in Q8?
3.
3.
No.
Sorry, not 3, 6, 6.
Yeah, 6.
Six,
Minus is also there. Yeah, perfect. So it's there are many order 4 elements. You can also compare order 2 elements. That's where it is. That's where the difference is kind of caused. There is only one order 2 element over there, and over here you have so many. And well, that's it. Basically, like this is the idea why group induction of this form won't work. Because this is a much simpler group, and you're getting much complicated groups over here. Still, you can write these groups and study. Imagine like I'm giving you a prime of very large order, say a 10-digit prime, and the next number after it is weird. Like it's not a prime, so it has factors, and you can get a non-abelian group. You have no idea what that non-abelian group. You have no idea how to factorize that number for that matter. So this is not how induction should work. So in groups, there are many ways to do induction. The best is to follow either of these two methods. One is the valuation or exponent of a prime, valuation at P. So you'll just look at this number where P is a prime, of course. Well, what is this number? This is basically defined to be the maximum over M. P per M divides size of G. So it can be 0 as well. Like if an M is greater than or equal to 0, by the way. So it can be 0 if P and size of G are co-prime. Otherwise, it's a natural number, like rather a positive integer to avoid conventional errors. And now you can use this, but sometimes you will realize that this is not the best measure. For example, G might have some associated primes as well, which are, or G is something like P Q power 1000 and R power 76 and so on. And this P might appear to be simple, but this seems to be very wild. That's why we sometimes look at two other methods of evaluating, essentially similar. One is capital V of size of G. It's basically the sum of all VPGs, where P divides size of G, which is also the same as sum over all primes, because if P does not divide size of G, then it is 0. And the other thing is the distinct primes, which is basically P divides size of G 1. So the number of distinct prime divisors, and essentially this is the same as VP over, or rather the capital V over the radical of G. If you remember your basic number theory, radical of a number is the product of all distinct prime factors. Okay. So these two generally work, and you can actually try to use these results and use these to prove some nice results. For example, to prove Cauchy's theorem for abelian group, you have a very neat proof using this fact. I won't prove it, but you can try to prove it using these things. Basically, if like your VG is 1, then it's done, right? Because it's Z mod PZ and it is cyclic, so it has an order P element. But if V mod G is, say, equal to M plus 1 or something, then you take, basically like G is not a trivial group. So take an element not equal to identity. And if like the order of A is divisible by P, the prime you're interested in, a prime which is dividing the size of G, then you can just look at A power order A divided by P, right? And that will have order P. Like it's some basic facts, right? This thing. Otherwise, the thing becomes interesting. And suppose P does not divide the order of A. Then because A is not trivial and G is abelian, you can just look at this group. And then it would have a lesser, like the V of this thing would be strictly lesser than the V of G. And then you can apply induction and use whatever result V, like that correspondence theorem, basically. So this is a very neat, important result. And because you have done it in the last class, I'll assume that you know Cauchy's theorem for non-abelian groups as well. But this is an alternate proof. And you can also give a proof of the Celo's theorem, which will state the abelian case at least. And I'll use this induction for P groups. So I've been talking about P groups quite a bit. So what are P groups? These are not necessarily finite, by the way. So we say G is a P group where P is a prime if For all A belonging to G, order of A equal to P power K, where K belongs to whole numbers. I'll use this notation for whole numbers because there is an issue with whether N is the whole numbers, like the or natural number contains zero and so on. Not if I give a zero, you assume that I'm assuming it's the whole numbers like 0, 1, 2, and so on. So this is what is called a P group. So of course, there are finite P groups. You have quite a few examples. Let's say, well, any Z P power NZ, their products. Then you have Q8, D8. These are all P groups. For that method, D 2 power N for any N greater than equal to 2. Sorry, not 2. Greater than equal to 4 because D4 is that group. So, and then there is V4, the Klein 4 group, and so on. Many examples. And you can see that they are not necessarily abelian. There are also examples of matrix groups which are P groups. You can look at the Heisenberg group, for example. Read about it later on. It's a very important group and it appears in physics as well. And this translation group, Euclidean translation group as well. So those groups are important. There are many P groups, but they need not be finite. For example, look at Z mod PZ X, which is the set of polynomials with coefficients modulo P. That's a group, right? Any two polynomial you can add and stuff, and well, this has a natural addition. So this gives you a group, and you can show that for any element A over here, P times A, or A power P, whatever way you want to write it, that's equal to 0, or the identity of the group. And if you do not like this example, there are many more examples. For example, you have seen what a direct product is. So you can just look at this and infinitely many times. Or the set of functions, which is basically or essentially the same as set of functions from the whole numbers to Z mod PZ. Or sequences for that matter, whatever you want to do. Like these are also P groups. But when G is finite, it turns out G has a nice structure. Finite P group, then the proposition is basically, this is not even a proposition, it's very obvious that size of G is P power L, where L is greater than equal to. Yeah, one convention is that we don't treat the trivial group to be a P group, because then what is P, you might ask. So I'll assume that G is not trivial whenever I'm talking about a P group. The size of G is P power L, PL is greater than equal to 1. So can you produce or give me a proof of this thing using whatever you know?
So if P, all the subgroups, the order of any subgroup of G will divide the order of G. But
Perfect.
the only divisors of P to the power L are powers of P. So, so if I take any element, then the order of the cyclic subgroup would be equal to the order of the element. The order of each element is a power of P, smaller than L.
Perfect. Okay, but there is a small problem. What you proved is basically if G is of this form, then it's a P group. That's what you proved, right?
Yes.
But I'm asking you to prove the converse. That is, if G is a finite P group, then it's of this form. Not if this is your group G, then. But it's a perfect realization. So basically, you'll get this is true. I should write it a bit properly. So you have actually proved this thing. This you have covered. If G, sorry, this you haven't covered. This you have covered. That if G, the size of G is like a power of P, then it's a finite P group. What about the converse? Well, it's not actually very hard. But you cannot do it just by Lagrange. Then maybe you can do it, but it won't be a very nice or easy proof. there. What you do is use Cauchy's theorem. So let A belongs to G. And then, of course, Lagrange theorem. So what I'll do is I need to prove this, right? So I can also prove not of this implies not negation of this. That is the contrapositive. These are equivalent. So I'll prove this part. So if G is not a power of a prime, and of course G is not trivial, then there are two distinct primes. Or that is, if G is not P power L, then there is a prime R not equal to P R prime, which divides the size of G. But that implies by Cauchy's theorem, there exists an A belonging to G such that order of A is equal to R. But R is not P power L for any L. And that immediately implies G is not a finite P group, or is not a P group. So is the proof clear, or the idea of the proof clear? Yeah, you might have to formalize a few more steps. I'm just giving you the concept here. Is it clear?
Yeah, it's fine.
Yeah. So all P groups have this nice structure, and sometimes in your undergraduate curriculum, P groups will be defined like this, that it has order, or this order of the group is a power of prime, not order of using order of elements. But that is a much more generic definition, as you can see. And sometimes when you do some more group theory, that's the definition which you'll need. Okay. So now I guess you are naturally interested to see what are the structures, or what can be the P groups. That's what today's class is about, structure of groups, right? So let's look at a few basic examples. We have already stated this has to be cyclic. What about this? Let me give you give me two examples of distinct P groups of size P square. You have already seen this. Think of it using P equal to 2, for example. Give me two groups of size 4.
So Klein 4 and the other cyclic group.
Exactly. And are these the only two groups?
Yes, these are the only two of size.
Perfect answer. Perfect answer. So first of all, these two are distinct examples because the latter is not cyclic. So for P, these two are two distinct groups of order P square. So we are naturally interested to see whether the converse holds. And as luck would have it, actually the converse holds. Like these are the only two groups of size P square. So if your order is P square, not just for any prime square, all groups are abelian, and in fact there are only two possible groups, this and this. So to prove it, I'll prove a much more generic result about P groups. If G is a P group, finite P group, then ZG not equal to 1. That is ZG is not trivial. So what is the proof? Have you seen this result, by the way? You have seen class equations, so maybe you have seen this result.
P groups weren't introduced in the last lecture.
Okay, it's fine. So basically the idea is very simple. What do you first of all, as I hinted, you write the class equation of G. N1 plus N2 plus Nk, where N1 is less than equal to N2 is less than equal to Nk.
So actually, I think this result was introduced in the last class, but the name P groups wasn't given.
I see. Yeah, that's fine. So tell me what the proof is. Let's just record it.
Sir, we use a class equation that the summation of index of stab A equal to mod ZG plus the summation of the index of centralizer of A.
Perfect.
And then mod zg is what we need to find, but the other two will be divisible by p. So this mod zg has to be divisible by p, but it is at least 1, so it's more than 1.
Exactly. Perfect answer. So basically, from our class equation, you have n1 is less than equal to nk, and ni divides the size of g, which is a power of p. Right? And who was it who answered this question? I cannot see who's speaking.
So Saraswata.
Saraswati. Perfect answer. So basically, what Saraswati is saying that, see, n1 has to be equal to 1, right? Because that's the identity element, and identity has no other conjugator. It's in the center. So saying that Zg is not equal to 1 is the same as saying n2 is equal to 1. If n2 is equal to 1, then the element corresponding to n2 is in the center. And center is not trivial. And if the center is not trivial, then n2 has to be equal to 1. Otherwise, like, there has to be one of these other than n1, which is 1. And that has to be n2, thanks to this ordering. But look at this closely. Ni is divided p power l implies ni is equal to some p power I, where I is greater than equal to 0. So you'll effectively get that p power l is equal to 1 plus p power, sorry, not p power I, p power some ki. P power k2 plus p power k3 and so on. But if k2 is greater than equal to 1, that would imply p divides basically p power l minus p power k2 plus p power k3 and so on. When that implies p divides 1, which is a contradiction. So you must have k2 is equal to 0. And that's the same as saying n2 is equal to 1. And in fact, because center is a subgroup, you will get size of center equal to p power some z, where z is greater than equal to 1. So using this, you can actually show that these are the only two. In fact, what is an immediate corollary over here is that any group of size p square is abelian. If size of g is p square, then g is abelian. And how to observe that is basically zg is not trivial. And also g mod zg can never be cyclic and not trivial. And if you don't want to go into those intricacies, like an easy way to look at this is basically suppose A belongs to G minus ZG. Suppose there is such an element. Then what is this? Sorry, maybe I should follow one standard notation. CG, the centralizer of A. This has to contain the center, and this also has to contain A. But A is not in the center. So immediately you will get the size of CGA, and this is basically not trivial. So this is the size is greater than equal to P. So you'll get this is strictly greater than P. But this is a subgroup and it divides the size of G. That would imply the size of the centralizer is equal to size of G, or if I just skip a few steps, that would show that the centralizer equal to G. But that's an equivalent definition of saying that A belongs to the center of G. And that's kind of a contradiction, right? So you can give a direct proof over here, the one which I was saying. But for the purpose of this class, a contradiction proof also works. We won't be getting too deep into it. So you'll immediately get that there is no such element and G is equal to ZG. That is, G is abelian. Now, if G is cyclic, it has to be like, because the size is P square, it has to be Z mod P square Z. The only case is if G is not cyclic, well, that's an exercise for you guys to figure out after the class. That is, if G, size of G is P square and G is not cyclic, so you have to prove using whatever you know that G is isomorphic to Z mod PZ cross Z mod PZ. Well, Now, some more facts about P groups. The non-trivial center was an important fact. Then you have, first thing is any group of the form PR1Z cross Z mod PR2Z and so on is a P group, right? Is it clear that this is a P group? You can use the equivalent form, by the way. Is it clear that this is a P group?
Yeah.
Okay. And then if G is a P group, and say H is also a P group, then G times H is a P group, first of all. If K is less than equal to G, then K is a P group. So any subgroup is a P group. And if K is normal in G, then G mod K is also P group. Quotients are also P groups. And you have a weaker proof of weaker statement, like weaker than Cauchy's theorem, that every P group has an element of order P. You can prove this without assuming Cauchy's theorem. And you cannot say anything about order P square. For example, as we just saw, this group has no element of order P square, even though the order is P square. In fact, for any P par K, you can find a group, just take products like this and K copies basically, and then you'll find an element or a group with P par K elements, but all elements other than the identity has order P. So the best you can say is about order P. Now what is interesting is you already know Lagrange theorem, that is, given any subgroup, the order of the subgroup divides the order of the group. What about the converse? Generally, it's not true. You might have heard this in the class where it was discussed. But for P groups, it is true. And something much stronger than Lagrange theorem holds over here. So the statement is, suppose size of G is P power n and L is less than equal to n, and of course greater than equal to 0. Then there exists a normal subgroup of G such that size of H is equal to P power L. Or even stronger, given any H less than equal to G, it can be any subgroup for that matter. There exists a chain of subgroups. So what is a chain of subgroups? Or a subnormal series, as we'll call it. 1 is equal to H0. So chain is not necessarily normal, but what I'm interested in is actually a subnormal series. So what is a subnormal series? I'll define it shortly. Just a second. Hn equal to G. Say the order of H is P power L. Then HL equal to H. And the size of HI is equal to P power I. So what is a subnormal series? Basically, the idea is a series like this, of a sequence of subgroups, like everything is a subgroup of everything. For example, you start with the trivial subgroup always. This is what is called a chain of subgroups. That is, H0 is a subgroup of H1, is a subgroup of H2, and so on. And it's called a subnormal series if HI is normal in HI plus 1 for all I. That is what I've written over here. If this happens, it's called a subnormal series. But mind you that HI might not be normal in G. I'm just saying for consecutive factors, this holds. Furthermore, if HI is normal in G, sometimes you are blessed with that fact. For example, in abelian groups. Any subgroup is normal in G. In that case, we call the group to be the series to be a normal series. So I'll state these formally later on, but just to know that these facts. So this is a subnormal series which I'm claiming. Okay. So is the statement clear? Whatever I made over here. So you can find a chain of subgroups such that the size of HI is P power I. If H is P power L, then HL is equal to H, and basically like Hn has to be G. So you can find a subnormal series of this form containing H. That's what I'm saying. And these groups, in general, for the general subnormal series Gi plus 1 mod Gi, are called the factors. Or composition factors is a much more general term, or much more specific term for that matter. These are called the factor groups. A subnormal factor or simply factors. Ith factor. Or I'll formalize this thing later on, but basically this is a factor. So if you look at these factors, what will the factor be? The factor is well defined because it's normal. So what is the factor? What is the size of the factor? Anyone? It is the same as this normal natural number quotient. And what is this size?
Some power of P.
It's a power of P, but specifically what is it?
It's P.
Look, it's P. And that implies what is H in this group?
Z mod PZ.
Exactly. So this is a remarkable fact. Like you can actually find a chain. And the proof follows from induction of groups. But again, this is just to highlight what the results are. You can try the proof later on. So I introduced induction so that you can understand how it follows and so on. So for example, for size of G equal to 1, P, it's obvious that the only subgroups are 1 and G, and this result follows. What if I'm looking at P square, verify from our cases, it's obvious. And then you can just use induction after that. Or even after 1, you can do induction. Very good. So now if you are convinced with this result, basically you get for P groups, the converse of Lagrange theorem holds. And in fact, another interesting result holds is, you remember this form. These were abelian P groups, right? These are abelian and P groups. In fact, what is true is any abelian finite P group is of this form. If G is an abelian finite group P group, G is of that form. G is of form as in part 1, right? It was part 1. The form 1. It was 1, most probably. Yeah. So, in fact, you can actually classify how many abelian P groups are there. So, for those interested in number theory or combinatorics, can you give me the number of abelian P groups? Where the size of G is say P power n. And these are distinct, by the way. If, like up to ordering, etc., you can show that these groups are distinct. And everything is of this form. So, effectively what you're doing is those R1 plus R2 plus whatever RK was there, you're adding it up to n, and I'm saying for each different kind of sum like this, and RK might large enough, like RK can be small, K can be small, K can be large. But these are free, like these Ri's are just greater than or equal to 1. That's the only thing you need. So what are these things called, and what is the set of all these numbers? Are you familiar with this thing? It is basically the partition of n. Number theoretic partition or simply partition of n. A number of you can write n as a sum of elements without considering the order. Sum of natural numbers. Sorry, not elements. Yeah. Okay. So perhaps you can try to prove these. If you want to know about it, feel free to contact me and I'll give you some references. I think there are some slides in net, proof of these results. But we'll head towards Celo's theorem and other facts. So let's just state the result. So Cauchy's theorem, you all already know. What is Celo's theorem? So basically, you've realized that, well, for any group G by Cauchy's theorem, like if you have a group G and P divides the order of G, P prime, then there exists a subgroup of size P, right? Or equivalently, there is an element of order P. There is such a subgroup. So the size is P. There is an element whose order is P. These are equivalent. But I said that there might not be elements of order P square even in P groups. So forget about general arbitrary non-abelian groups. These non-abelian, by the way. General, just a finite group. So perhaps I can't get elements, but I can guess that if say P power K divides the size of G, I can get a subgroup of size P power K. Well, in P groups, I could do that, as I said. So my guess is for arbitrary groups, I can do that as well. And indeed, that's the case. So I'll define what a Celo P group is first. So it's basically a P group which is maximal. So a Celo P group is basically an H less than equal to G such that H is a P group and the index of H in G is co-prime to P. That is, if size of G is say P power L times M, where M comma P equal to 1, you can always write a number like this. If P is dividing G, then size of the Celo P group H is basically P power L. So any group of this format is a Celo P group. But a priori, there is no reason for such a group to exist. That is what Celo's theorem tells us. And the theorem basically tells us in 3 parts. I'll briefly summarize it in one go, like in one sentence. But the statement basically tells us that, well, you can do all these things and all these facts, assuming that there is a P group. And in fact, there is a P group. That is what the statement tells us. So if P divides the order of G, then there exists a Celo P group of G. And in fact, that would imply by our result on subgroups, you take the subgroup of the Celo P group, and then for all whatever I was interested in over here, then if P power K divides size of G, there exists an H subgroup of G such that size of H is P power K. This is the first part of Celo's theorem. The second part states that all such Celo groups are conjugates. In fact, what it does is basically give me 2 Celo groups, Celo P groups, P subgroups. So I was saying Celo P groups, but it's the same thing, like Celo P subgroups, because it's a subgroup of G at the end of the day. Then there exists a G belonging to G such that GS1 G inverse is equal to S2. And this has another related fact, that is, given any H, a P subgroup, that is, H is a subgroup of G such that the order of H is P power K, there exists a Celo P group containing H. That is, H is less than equal to S for some CeLO P group. So any P group is contained in a larger CeLO P group. So that's actually remarkable. So without assuming anything, you are showing that CeLO P groups exist, and also like any subgroup, any P group is contained in a CeLO P group. So it's kind of it's not exactly the converse, but it's kind of related or to the opposite sentence, or kind of a converse of the first part. Like of the first part is the corollary of the first part is giving you that if the P par K divides G, then H is inside G, and in fact H is inside a CeLO P group. What I'm saying is any H which is a P subgroup of G is inside a CeLO P group. And the third part is of combinatorial or counting relevance. That is basically if there are K many CeLO P groups, it has to be finite, because in a finite group, the number of subgroups, the number of subsets is finite. So the number of subgroups is also finite. So if there are K many CeLO P groups, and if, as I wrote back then, this is true, where P does not divide M, then you get K is congruent to 1 mod P. Basically, this should also give you the first part in this sense, because K is congruent to 1 mod P, cannot be 0. There is at least one P group. And also K divides M. And perhaps a very easy exercise is that if there is a unique CeLO P group, like if K is equal to 1, that implies that CeLO P group is normal in G. Why does it follow? Anyone? Just from the statements? And the hint is to look at 2.
So S1 and S2 are equal. So by definition, S1 is normal.
Exactly. So given a CeLO P group S, of course, GS G inverse is also a CeLO P group, because the order of GS G inverse is the same as S. So it's also a CeLO P group. But I said there is just one. So this has to be true. It's kind of the converse of 2. Like, as I said, these are not converses precisely, but kind of in the opposite direction to 2. 2 is giving you that any two things are like conjugates. What I'm saying is a conjugate is a CeLO P group, and using that uniqueness. And this is also a very important fact while you classify groups and so on. Brilliant. So now, perhaps, would you prefer a break, or should I continue to the end? Like because we started around 5:45, so I'll go till about 7:15. So would you prefer a break right now? A tea break or something? What's the general opinion? Okay, so if you have the energy, I'll continue. Okay, so now you have Celo's theorem. So for abelian groups, this becomes kind of fascinating and also degenerate. Like, it's very easy. CeLO for abelian, I'll call it. Now you look at 2. And 2 says that any two CeLO subgroups are conjugates, right? And actually, by 2, if K is equal to 1, if and only if this holds. Like, by 2, this is also true. But any subgroup of an abelian group is normal. So the CeLO P group is unique in an abelian group, no matter what your group is. So given a G abelian finite, and P divides the order of G, there exists a unique CeLO P group of G. In fact, you call that SP maybe, because it's unique, you can call it SP. You will get that G is isomorphic to the direct product of, sorry, not I equal to 1. P divides G SPs. So how do you do this? Well, have you learned about internal direct products in your past classes? Like external, I think you have dealt with. The internal is basically if you have H and K subgroup of G, when can you say that HK, the product subgroup, is like it's not necessarily a subgroup, it's just the element HK. But when can you say that this is a subgroup and this is isomorphic to H cross K? Have we seen this thing before? If not, read about it later on. I won't be getting into it, but using that, you can prove this thing. And this is pretty remarkable, right? You're not just telling that there is a unique, which itself is fascinating. For any P, it's unique. You're also telling that G is a direct product of such groups. And direct products are like what should I say? The neatest or the easiest to analyze constructions on groups. Like if you have a set of groups, the easiest to analyze constructions are direct products. It's just like orders and Cartesian product and just component-wise operations. Like these are like the neatest or prettiest things to deal with. Well, that's what you get for abelian groups. And as a consequence, you have the fundamental theorem for finite abelian groups. Finite abelian groups. Some old texts also call this the fundamental theorem for group theory finite version, but we'll call this one. And use this and the fact that because SP is a subgroup of an abelian group, so it is abelian. So use that. It's an abelian P group. Use the characterization of abelian P groups, and basically you'll get G is isomorphic to direct product of cyclic subgroups, or just cyclic groups if you are not interested in subgroups, cyclic groups. And not just that, in an almost unique fashion. That is, of course, you have this thing. So of ordering does not matter, but if you remove the ordering, the direct product is unique in a unique fashion. Just like prime factorization, you are not interested in the ordering, or for that matter, the signs. If you call minus P to be a prime when P is a prime, if you define it like that, then you're not interested in that, P or minus P. But if you remove those two things, fundamental theorem of algebra tells that the factorization is unique. Even here, it's true. But this is not so neat in the non-abelian case, because any such group is abelian. So how can you get non-abelian groups using this kind of a trick? But the next target of today's class is to talk about non-abelian groups and how to have a structured theorem over there as well. So till this point of today's talk, is everything clear? The basic ideas, like even if the proofs you can think about them later on, but the basic ideas, are they clear? Like, are those ideas clear?
Yeah.
Perfect. So if that's the case, we'll briefly discuss what are...
If you have the time, can you just recapitulate quickly once? Like in 5 minutes, can you recapitulate once?
Surely. Why not? But if the timing kind of overshoots, is it fine with you guys? Like, it's fine with me. It can go on a bit longer.
Yeah,
but...
it's fine with us.
Yeah, we are all free, I think.
Oh, then it's fine. No problem at all. So we have covered, maybe I'll call this session 1 and give a yellow color to this. You have seen these things and this. I'll come to this later, even though it's given for this. And also briefly this thing, but I'll not take it right. So conjugacy and class equation, it's fine. This was kind of a recap. So conjugate is basically anything which is a similarly behaved element. So if you look at a function, it's basically you have A over here as a function. Like group elements can also be thought of as functions, right? So if you look at this, we say it's kind of conjugate if you can go to this other part, do the operation over here, and then come back. And that's basically a G. You play a G first, go over here, and then you go. Sorry. The arrows might be a bit different, but basically that's the idea. So you go through a G and you go through a G inverse. So I think this should be A and this should be B, yeah. Because B is this thing. So that's kind of the idea of conjugate. Like they are parallels in a sense. In the group, if you draw the group, they are kind of parallel functions or parallel elements, same properties. So hence, it's feasible to define an equivalence relation using them, and you get conjugacy class, the class equation, centralize the duality, like centralize the conjugacy duality, and you have some nice corollaries to the fact. And also, it's not just restricted to elements. You can also talk about conjugacy of subgroups. That is, look at this conjugate subgroup. And then you can see that this is also an equivalence relation. And, well, if all the conjugates are same for an element, we realize that it's in the center. And anything in the center satisfies that. And for all the conjugates of the subgroup to be the same as the subgroup is the same as H being normal in G. Then we talked briefly about the correspondence theorem, which gives us using this diagram, a very neat correspondence between the subgroups of G mod H to something which is better known. That is subgroups of G, which also contain H. This is easier to study. But if I give you a very weird quotient, like 2-3 quotients together and so on, like that's harder to study. But this is very, very easy to have, sort of analyze. And this is kind of the correspondence that K goes to K mod H. And if you have a subgroup over here S, then you trace it back and take a product of S with H. So that's kind of the idea. And we recall these concepts and few examples. And I kind of try to motivate why induction is not feasible in the linear fashion or using the natural ordering. So the induction which we do is using a valuation or a function which is satisfying some nice number theoretic properties. For example, this function is additive, right? VP is additive. That additive means basically this thing. M plus VPN. This is true, right? And using that, well, you get some neat properties, and you can define a few valuations of interest. For example, VP, which is the prime exponent of the prime in the factorization of size of G. These are true for natural numbers as well. Like I'm just giving it for G, you can do it for natural numbers as well. And then capital VG is the total number of prime, how many prime factors are there. DVG is the number of distinct prime factors. So these are kind of what we discussed, and then I gave you a hint or like an outline of how you can use these. And the first application is to prove Cauchy's theorem for finite abelian groups. And then we headed to P groups. And what are P groups? A group where every element has an order which is a power of P. The P is a prime. Of course, I forgot to mention this, but if you take any natural number n, and when does it make sense to talk about n groups? Anyone? Any answer? Like it's... yeah, what's the answer?
No, I was asking for you to repeat once what you just asked.
Like if n is a natural number, of course, one group does not make sense. If n is greater than or equal to 2, then when does it make sense to ask like, makes sense to call a group an n group? Every element is a power of n. That's what I want to say.
Only when n is prime, I think.
Exactly. Only when n is prime. Because if there is an element, or like if n is not a prime, then
there
you
is some other prime.
Exactly. And you can just take a prime dividing n. And because any element has order which is a power of n, or at least which divides n, which is divisible by n, sorry, you can find exactly an element which has order that prime, which is dividing n, the prime which we are interested in. And that would contradict the definition if n is not a prime. So yeah, it only makes sense to talk about P groups. And then we proved a few basic properties about P groups. And that is, if G is a finite P group, then it's equivalent to the order of G being a order. So order of elements being power of prime is the same as order of G being power of a prime. And we proved a few basic facts like in a finite P group, the center is non-trivial. Then we also showed using this, or rather hinted that, showed that any group of size P square is abelian, but what are the, and I claim that there are only two possible groups, and you can verify like from whatever I stated later on that these are the only two ways you can factorize it, right? Using the fundamental theorem. Well, prove it. You don't need to use fundamental theorem. In fact, the proof of fundamental theorem, the way we, or way I hinted in this talk, relies on this fact in a sense. Perhaps not exactly this fact, but some later facts. This one, precisely the point 6, which I stated that any abelian P group, finite abelian P group is of this form. And then here are a few basic facts about P groups. Well, very simple. These two are kind of interesting. That is, given any L less than equal to N, or that is the same as saying any divisor of G, order of G, you can find a subgroup of that size. And you can extend this further and say that you fix me a subgroup. Like over here, it's your only fixed thing is G. And then I'm just finding a subgroup. But in the next case, I'm telling you give me a subgroup and I can give you a path of subgroups in a sense, going from 1 to G, passing through this H. And the increment is always fixed by P. And such paths are sometimes important because these are invariants or stuff like that. So this is something which is called a subnormal series. And that's what I claimed. In fact, the funny part is you can, for this group, you can sometimes also claim that there is a normal series. But then you will at least need that H is normal in G, right? Otherwise, how can anything else? Because H is a part of the series. A normal series is a subnormal series in which every element is normal in G. So those things would require some careful analysis, and I'm not well into that. Perhaps it's for you to read later on. And what we showed is the factor groups, like hi plus 1 mod hi's, because the increment is p and it's subsequently normal, like hi is normal in hi plus 1 and so on. You'll get this thing is true. And this is very nice. That is, all the factors are cyclic. And as I claim that any finite abelian P group is of the form stated in 1, and you can show that that's the same as the number of distinct, non-isomorphic, not distinct, just non-isomorphic P groups is equal to the number of partitions of N. And then I stated and studied the Seedo's theorem. Well, you can look at the theorem. It basically says that for our interest, it basically says that given a P power K, or rather a prime power dividing the order of Z, you can find a subgroup. So it's a direct generalization of what we did for P groups to general non-abelian groups. And this is of course true for abelian groups as well. Like it's true for any group. And I stated a few statements, and then that CeLO P groups are conjugates and some corollaries of that fact. And for abelian groups, it just gives us something much stronger, that G is isomorphic to the direct product of all these CeLO P groups. And fundamental theorem for finite abelian groups is just merging CeLO's theorem for abelian groups and the structure theory for P groups. That is because any P group is the direct product of cyclic groups, and any abelian group is the direct product of CeLO P groups. Any abelian group is the direct product of these abelian over here. Any abelian group is the direct product of cyclic groups. Not just that, in a unique fashion. So is it clear? So should I, or perhaps I will take a short break and then I'll continue.
Thank you.
Feel free to ask questions. I'm here. Okay, hello everyone. Am I audible?
Yes.
Okay. In that case, I'll resume. So, any further questions? If not, I guess, yeah, let's continue. So, the structure for finitely generated groups is harder. Have you seen finitely generated groups before? No, finitely generated abelian groups. Let me clarify. Like, what do I mean by finite generation?
So I don't know the exact definition, but does it mean that every element of that infinite group can be generated using a finite set of elements?
Exactly. That is the idea. So basically, we say a group G, in general, a group G is finitely generated if there is a finite set of elements S1 to Sk such that the subgroup generated. Have you seen this subgroup generated concept? Have you seen this?
Not in these lectures.
I see. In that case, I think I should not cover this thing. You can read it up because you need to know what generated subgroups are. And I think that is something you should know. So, the subgroup generated is the smallest subgroup containing all these elements and is the same as take all possible compositions of these elements and their inverses. That's
Yes,
the same.
it has been discussed in the number theory course, I think.
Oh, I see. I see. Nice, nice. In that case, yeah, you can refer to that. Otherwise, I think this is kind of a reading exercise. You don't need to know the proofs because that's harder. You'll need some model theory to make sense of a few facts. But reading exercises would be one, generated subgroups, and symmetric sets, because these are of relevance in number theory, for example, you said, and physics and so on. And these are basically symmetric set is kind of this is the logic. If X, their set says that X belongs to S implies X inverse belongs to S, closed under inverses. And multiplicative sets are the opposite in the sense, not the opposite exactly, like X belongs to S, Y belongs to S implies XY belongs to S. This is multiplicative sets. And if something is both a multiplicative set and a symmetric set and is non-empty, what is it?
A group.
It's a subgroup, precisely.
Yeah, subgroup. Okay.
Yep, exactly. But yeah, it's a group, and that's the logic. And the other thing is finitely generated abelian groups. Basically, some infinite abelian groups have some nice structure. For example, Z, right? It's cyclic. Z square. What about Z square times Z mod nz? Even though it's infinite, it has a nice structure, and you can study it using these two parts distinctly, right? Using this separately and this separately. That is the idea. This is called something called a torsion group. Basically, if you have a group G, maybe I can state this. And this is something relevant to algebraic topology and topology as well, if you do it later on.
My understanding of something with you.
Yeah, once again.
If you've got an abelian group, you can split it into a free abelian group and a torsion abelian group. And if the torsion abelian group has order p1 to the power r1 times p2 to the power r2, blah, 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 you can write it as the direct sum of abelian groups with orders p1 to the power r1, another abelian group with order p1 to the power r2, and so on. And those individual groups can be written as the direct sums of cyclic groups, cyclic abelian groups. Is that correct?
Exactly. That is the idea. Perfect answer. That is actually the structure result. I think I can state the structure result as you did so. But you need to know what finitely generated abelian groups are to make sense of that. So a finitely generated subgroup is basically like there it has kind of a generating set. Like if you know some linear algebra, you know what a spanning set is. It has a spanning set inside the group. Like everything can be written in terms of those symbols and their inverses. That's basically what a finitely generated abelian group is. And you can extend this result to finitely generated groups. That is, any G is isomorphic to the direct product of cyclic groups, include Z as well. Now, in a unique fashion, like all the Z's club together, and there are, the number of Z's. It's called the number of Z's is called the rank of G, or the free part of G for that matter, because Z has no relation. Like there is no order, right? It's just a group of elements. For every power, you have a distinct element. So it's free. And there is a torsion part, which is a finite group in that case. And the torsion group is basically, I'll define that shortly. If G is an abelian group, tor G is basically defined to be all A belonging to G such that the order of A is finite. You can show that this is a subgroup because as G is abelian, order of AB is bounded by order of A, order of B. In fact, the LCM does the job as well, but I just need to show it's finite. Right?
And this is just a special case for modules, right? Modules have a principal ID of domains in general, right?
Exactly. That's what I meant to say. Like to make sense or understand the beauty of this result, this is also true for modules over principal ideal domains. Perfect answer. So it's wonderful to know about these. So these two are true, and you will get this is a subgroup. And what's further true is this fact that G is isomorphic to. This is not generally true that if H is normal in G, then G mod H. The direct product of G mod H and H is the same as G. This is not generally true. For example, Z mod 4Z is not the same as, and Z mod 2Z is inside Z mod 4Z using 2Z mod 4Z. But it is not true that it is isomorphic to Z mod 2Z cross Z mod 2Z. But over here, because of this distinctive nature, one has finite order elements and the other is kind of free, or there is no relation. You get G is isomorphic to G mod tau G times tau G. And this is called the free part. And this is called the torsion. And over here, this is isomorphic to some Z power R. You can show this. And this is a finite abelian G group. Apply this R theorem to this part, and well, this is here, R is called the rank, and you get a lot of things. But this is a reading exercise. I won't get into it. But wonderful that you know a bit about modules and things. So this helps out because any Z modules are the same as abelian groups. Any module is an abelian group, but Z modules give you no extra information for that matter.
Can I ask you a question about something that's not quite related to this?
Yeah, surely.
I was reading about flat modules, and I think I have an okay understanding of the algebraic intuition behind them. But the geometric intuition escapes me, and I don't know any algebraic geometry. So could you, if it's possible, could you give me some very brief intuition to it about flat modules? The geometric intuition, I mean, not the algebraic.
Okay, I see. So should we revisit this part after the talk? I think the others might feel left out because that's not something which we have covered. Say about 7:30, or you can mail me if you want to. I'll give my mail address towards the end. You can mail me later on. We can schedule a meeting or discuss about it later on.
Okay, thank
Perhaps?
you. Thank you very much.
Okay, yeah, surely. You're most welcome. So let's continue. And as I said, now we'll focus on what is called the composition series, the thing which we were interested in. So if G is abelian, we almost know everything about the group. That is, as soon as you can factorize it as the direct product, well, this is easy to study. And you get a lot of information, and this is no longer interesting. We have solved this problem. What if G is not abelian? As I said, it need not be direct product of course, it's not direct product of abelian group. It's also not necessary that it's a direct product of known groups in the sense, simple groups. Not simple groups, simpler to study groups. So we kind of generalize what we stated for P groups. You remember this fact? For P groups, we did that if G is a P group, not necessarily abelian, then you can find this chain. This is equal to H0, less than equal to H1, and so on. Hm, which is equal to some G, such that each Hi minus 1 is normal in Hi. And you also have the size of Hi is equal to P power I, where the size of G is P power M, of course. You know this. Like we stated this part. There. And also, like P groups, we have kind of categorized, not exactly categorized all the P groups, but we have like briefly discussed, like there is a nice structure. This is a structure for P groups, or that there is the converse of Lagrange theorem over there. The similar result, if I briefly, the other way I wrote this thing is basically each Hi mod Hi plus Hi minus 1 is isomorphic to Z mod Pz, which is basically a cyclic P group, or one might call it a, what's better, it's a prime order group. So prime order groups are interesting because they have no other subgroups, right? The subgroups are the trivial ones, that is 1 and the whole group. In fact, you can show that if like these are the only two subgroups of a group, then it is a prime order group. That's not hard to see. Like, I'll leave it as an exercise. If G has only two subgroups, one and G, then the order of G is a prime. Of course, the thing is, yeah, for infinite, is it? Yeah, even infinite, I guess it's true. Yeah. But let's just deal with G finite for that matter. But I think it's also true for infinite. Yeah, of course it's true for infinite. You just prove it for finite. That's more than enough. So these are the simplest groups in the sense, like easiest to study groups, just two subgroups. So I claim that such a similar thing is also true for abelian groups. And the proof is like very obvious. In fact, I'll call this property, say for now, I'll call it a good property. So my claim is if G is a good group, G1 and G2, both of these are good, that implies G1 times G2 is also good. The only thing is you cannot stick to this P. You have to remove the P from the definition. I have to just look at this prime order group. So every factor, these were, for, as I said, these are called the factors. So every factor is of prime order. So my claim is if G has this, G1 has this property and G2 has this property, then G1 times G2 also has this property. So can you give me a proof? I'll give you like a few notation just to ensure that we are on the same page. Is equal to G, ladder 1, top, and also this is true. Maybe it's not K, it's some L. And what I'm saying is we call a group is good if such a chain exists such that this is true. Is a prime order cyclic group. So let me just give you a few examples which are not P groups. Take G to be. Say Z mod 6Z. Or to avoid some notational conflict, I'll call it C6, the cyclic group of 6 elements. Then can you give me a chain of such groups? Any chain would do. There might be more than one chain. Just give me one chain. Anyone?
The first element is C3.
Yeah?
Can the first element be C3?
Exactly. The first element is always like identity. And then C3.
No, I was
And then?
going in the opposite order, sorry.
Okay.
C6.
This?
Yeah, seems fine, but I haven't checked.
It's perfect. Yeah. Another example is this. In fact, these are the only two examples.
C2, C6.
Exactly. So what are the quotients over here? This one is, the quotient is basically C3, and over here the quotient would be, because C6 is abelian, quotients are always defined, this is C2. Over here the order is flipped. This quotient would be C2 and this quotient would be C3. But these are still the same. And also they are cyclic prime order. So it's a good group. But are all good groups either P groups or abelian? That's not the case. Look at S3. And over here, one is normal in A3, which is normal in S3. In fact, unfortunately, this is the only case, because if something non-trivial is normal in S3, then it has to be A3. That's true. The order 2 subgroups are not normal. But nevertheless, you have a factorization. Over here, you will get a C3. Over here, you will get a C2. So the factorization is not necessarily unique. That's also one thing. And also, there were many P groups of the same order, but the factorization was always all P's. But you can get a factorization even for non-abelian groups. So for P groups, now just look at some larger groups. Say, try to look at S4, for example, or A4, or whatever you want to do. But unfortunately, you cannot always do this. As we'll see shortly, I won't prove it, but I'll state a result that A5 does not have such a neat factorization. In fact, A5 is not cyclic. Yeah?
Is it simple?
Yeah, it's simple. It's simple. In fact, A5 has no non-trivial normal subgroup. So it's very closely related to this prime order. It has no subgroup over here, but over here there are subgroups of A5. Just they are not normal. Hence, you cannot do such a thing, right? Because the last part is normal it has to be normal in A5. But A5 is not cyclic and you cannot do it. So perhaps you can easily observe that this is true. The product is good. And the idea is basically you look at this, and I'll call it as 1 cross 1, which is normal in H01 cross 1, which is normal in H1, this is H01 plus 1. I'll state it in the next page. So basically, 1 cross 1 is equal to H1 cross H02. This is normal in H01 cross H12, so on. Just continue this process till you reach your HL2, and then just increment the first coordinates. That is H11 cross HL2, and so on. And that's not a very hard thing to do. And you'll end up with G1 cross G2. So basically, like if you look at, there was this chain on from like you want to end up at G. Say I draw a diagram. So this is your G1, this is your G2. There was a chain of steps. Such a chain exists. Such a chain exists. From 1 you can go to C3 using these small increments. And G1 cross G2 is somewhere over here, right? So what I'm doing is basically I'm following this path first, and then I'm going this part. You can also go this part first and this, but well, you can shift it over here and just complete the proof. That's my idea. So is the idea clear that in fact G1 cross G2 is good?
Yeah.
Okay. In that case, an immediate corollary by the fundamental theorem for abelian groups is that any abelian group is good. Any abelian finite group is good. So not just P groups, in fact, abelian finite groups are good. S3 is good. As I said, S4, A4, all of these are good. And many more examples of good. In fact, like nearly like all of the simple examples which you know are good, other than, as I said, AN and stuff. So such groups are very close, or what should I say, very closely associated to abelian groups, and these are called solvable groups. So you can kind of solve or find a solution to these groups using this factorization. Instead of product factorization, because product might not make sense, you use a quotient factorization, chain of quotients. Yeah, is anybody telling something? I think it's not audible. Could you just speak a bit louder? Actually, your voice is not clear.
Isn't the term solvable related to, right? Hello?
Yeah, could you just repeat once again? Actually, your voice is, the volume is very low. Is it Ishan who speak?
Yes, Snehinh. 1 second.
Okay.
Can I post my message in the chat?
Okay, surely. If anybody could read it out, or you can. Your voice is better now. Like, could you just repeat once
Isn't
again?
the term solvable related to like concerns in Galois theory?
Exactly. I was about to relate to that soon. Like, why is it exactly called solvable? So there is this beautiful branch of mathematics. Basically, it follows from all of basic abstract algebra called Galois theory. It requires everything, but it kind of came first. It's basically a correspondence between the structure of groups and the structure of field extensions. What are field extensions? Like, if you know what fields are, two fields and there is a containment. Like, if F1 is a subfield of F2, then it turns out F1 kind of generates a vector space structure on F2. That is, F2 is a F1 vector space. And then you can use that and study polynomials. Or even if you forget about fields, look at R or look at Q, because R is boring. Look at Q. So you are interested to see when you can give a formula for the roots of a polynomial over Q. And we call those like polynomials, and there is a group associated to those polynomials, thanks to the roots of the polynomials. We call those as solvable, if you can write it. That's it. And it turns out you can do that if and only if your group is kind of solvable. So that's why it's also called solvable. So thank you for pointing it out. That was a very nice point to bring up. Okay. So now to make more sense, and I'll just give a few definitions. As I said, I'll formalize the theory. So this thing which I've been writing again and again, this is called a series or ascending chain. Sometimes you start with G and go towards 1. That's also interesting, but you won't be dealing with that. If Ni is normal in Ni plus 1, we call this, for each I, we call this as a subnormal series. And Ni mod, because we are starting with a 0, Ni mod Ni minus 1 is called the ith factor. Or just a factor. Like, these are called the factor subgroups. So first was this, second is this subnormal series definition. Sometimes it happens that these factor subgroups are abelian. In that case, we call G is solvable. But we just gave another definition of solvable, that these factors are not just abelian, they're cyclic. So are these the same? Let's think about it once. I'll come back to it.
Cyclic is stronger than abelian.
Cyclic is stronger than abelian. But I'm saying that they are the same.
Yes, if it's abelian, then you can add factors, right? In between, make it.
Exactly, that's the idea. Using the correspondence theorem, abelian group, any subgroup is normal, and abelian groups are good. So just add the factors. Perfect. So next is, sometimes you're not just satisfied with Ni being normal in the next component. You want Ni to be normal in general. If Ni is normal in G for all I, we say G is, and of course, and sorry, wait a second. If Ni is normal in G, then not G is. We say the series is like subnormal series is when like Ni was normal in Ni plus 1. We call this a normal series or an invariant series. Again, like it's an easy fact that every group has a subnormal series and a normal series. Can you give me one for any group?
One and G.
Exactly, like that's the trivial example. This one. So every group has a normal series or a subnormal series. Perfect. And like we are also interested in when it is abelian. So if the factor of a normal series, normal plus solvable, that is factors are abelian, we call such a group to be super solvable. Like it's like very nice in a sense. And sometimes instead of generalizing this way, we are also interested in something called, or rather I'll generalize normal series further and I'll say that, well, I know one case in which a group is normal in G. Can you give me an example of a subgroup which is normal in G? Which is always normal in G, other than one. And like it might be one as well, but in general, like sometimes it's larger.
This
Yeah, exactly. Continue.
is like G a random group or something?
It's not random, it's arbitrary.
Yeah. Sorry, arbitrary.
Yeah, okay.
Then I
So-
know that any subgroup with the smallest index must be normal, but I have.
Yeah, that's true. No. Smallest index must be normal. Is that true? Okay, I'll just think about it maybe later on. If smallest prime index. Yeah, that's true. Yeah, it would also follow. Of course, like if there is a smallest index. Okay, nice, correct. So, but I'm interested in something simpler. It's basically ZG is normal in G, right? This might be one, as I said.
Normalizes stuff like that.
Exactly. I'll just look at the center, like the simplest stuff.
Okay.
The center might be 1. So this is a very special case of normal sequence in which what's happening is, if you look at this, because everything is normal, so I can expect the Ni plus 1 mod Ni. It's not just, it is because it's a normal sequence, it's normal in G mod Ni. But I'm expecting it's actually a subgroup of the center. ZG mod Ni. And that would imply it's normal, but this is much stronger. In fact, by induction, a normal series, the whole definition is much stronger than a normal series. Such are called central series.
Are you going to talk about commutators now?
Yeah, I'll come to commutators soon. But I'll not go deep into it, but yeah, I'll define what commutators are. So this is called a central series. Precisely, it's like there are many names of the central series, like upper central, lower central. So I'll just call it a central series. And if But the problem is all groups do not have central series. Like this is too much to assume, right? For example, yeah, like it has a central series. Like it's not necessary that it would stop or like you can reach to G in one step. So, well, perhaps, for example, just look at this one. A5, as I said, A5 is simple. Like it has no trivial normal subgroup. So your N0, N1, everything will be 1 and you can never reach A5. So that's kind of a problem. But if you can reach A5 and there is a central series with some good factors, see over here it has to be abelian, right? Because it's in the center. So we say if a group possesses a central series, we call such a group nilpotent. But for what is the motivation behind this definition? It would require some advanced algebra to understand. I just wanted to include it because it's very close to what we are doing. So hence it was included in this talk. So let's return to solvable. So perhaps it's also important to talk about composition series. So what is a composition series? Well, if you have a series, if you have a length, mathematicians want to optimize it. Like how large can you go? Over here, the smallest is known, 1G. So the natural question is how large can we go? So composition series is simply a subnormal series of maximal length. So you take all the subnormal series, whatever is possible, it's also finite. The number of subnormal series is also finite for a finite group. And you take the one which has the largest length. That's what is called a composition series. Likewise, a chief series is a normal series with maximum length of max length. These two have to exist, as I said, because there are finitely many composition series and chief series. So one has to have the largest length. So the idea is, as I said, for solvable, there I said that there is a cyclic one. And it turns out the following are equivalent. That is G solvable, the way we defined it later on. G has a subnormal series with cyclic factors, the stronger one. And finally, G has a composition series with abelian factors. And in fact, because it's a composition, you cannot increase the length further. So all these abelian have to be cyclic in a sense. So this is more than enough. Wonderful. So is the definition and the idea clear behind what composition series and solvable and subnormal series, these things are? These are very important. Or should I repeat anything? If not, I'll continue. I'm assuming it's clear, and if not, like you can just revisit. The definition of a series is easy. Subnormal series is I'm just assuming I need to take quotients. So this is the least I must assume. And if the quotients are abelian, best possible, I call G to be solvable. Next, I am like mustering some courage and I want to say, no, I want Ni to be normal in G. Well, that's also possible. Every group has such a series, and such a series is called a normal series. So if the length is maximal, for subnormal we call it composition. For normal we call it chief. And if normal and solvable hold together, we call it supersolvable. In fact, for supersolvable, using whatever I stated below, you can show that the following are equivalent and continue over there. A similar following, a statement of equivalence for supersolvable groups as well. And finally, this is the boldest step where I am saying that everything is in the center of the whole group, the quotient. And that's what gives you what are known as nilpotent groups. Well, we won't require nilpotent, but these are all the important or basic series which you'll need. There are many more series. in groups, and you can understand like the series are the things which is the best you can expect. You cannot expect a factorization of product. Series is the best you can expect. So that's what you get. Okay. So how to check whether a group is solvable or not? That's generally hard. How can you find the subgroups? You don't even know if it's a subgroup. Or if there is a subgroup such that G mod H, like the second last should be such, last is G, the second last should be such that if you take modulo that group, G must become abelian. So finding such groups are hard, and you even don't know whether such a group exists. That's why we need something called the concept of commutator to realize that, well, how large or is there a quotient which is abelian? So I'll define what a commutator is. Have you, does anybody over here know how to solve a Rubik's Cube? Has tried to play with a Rubik's Cube?
I do.
Okay.
Never.
Okay. So have you seen moves like this?
Yep. They're very, that notation is very familiar.
Okay. And that is what is a commutator. Basically, we define the commutator, let x comma y belongs to G. Then the commutator xy is defined to be x inverse y inverse xy. Some books or old books define xy x inverse y inverse. So this is better in a sense. And this is helpful as well. Like you can multiply, for example, x times x comma y would be an associate, like a conjugate of x and so on. Like these are nice things. Likewise, y, you can get a y and show that it's also a conjugate of y times xy is a conjugate of y, and that's better. But okay, I'll follow this notation, and this is called a commutator. So you can immediately observe that this holds if and only if x and y commute. Also, if say h is normal in G, then x comma y h, this element is the same as x h or y h. As cosets or whatever quotients, whatever you want to call it, this is true. Just use the property. So suppose there is an h less than equal to, or h, a normal subgroup of G such that G mod h is abelian. That would imply xh, yh is equal to 1h for all x comma y belonging to G. That is xh, yh belongs to G mod h. But that implies xy, h is equal to 1h. So what is the implication? What is the implication over here? If an element times h belongs to 1h, that's the same as saying this xy belongs to h. Basically, it's the identity. I'm saying that something is the same as the identity, so it has to belong.
Quotienting it by the alien, right?
Ishan, I didn't get you actually. There was a lag.
Might be wrong. I'm not thinking very clearly right now, but quotienting by the commutator makes the group abelian, right?
Yeah, that's what I'm headed to. So basically, if G mod h is abelian, then x comma y belongs to h. And in fact, look at it closely, you'll realize that these are all if and only ifs. This is abelian if and only if this is true, and so on. So G mod h is abelian if and only if I'll call something to be G prime that is inside H. And what is G prime? G prime is defined to be the subgroup generated. Like I thought you know what subgroup generated are, but well, it is the subgroup generated by all the commutators.
Why can't we just define it as the smallest subgroup containing all the elements?
Yeah, that's what the definition of subgroup generated is, right? Like equivalent definition of a subgroup generated is that it's the smallest subgroup containing all these elements. But you can give a very concrete characterization. Like that smallest subgroup is kind of what is it, a universal categorization. But you can give a concrete characterization as well. Like this is how it looks. The tensors have a very universal categorization or universal property to define tensors as well. And there is also something called like that. As you said, modules. I'm assuming you
The
also have flat.
Kronecker product.
Exactly. So
Yeah, you
over
were
here,
talking about. You were talking about concrete representation of tensor products, representations of tensor products, right? Did you mean like stuff like the Kronecker product or something like that? I don't
yeah,
remember the
exactly.
name exactly right
Yeah,
now.
it's same over here. But yeah, that's basically the concept. So, but let's forget about that. And this is basically, as Ishan pointed out, this is the smallest subgroup containing all such elements. So as I said, you can give a very concrete realization of this thing using the compositions. Like take these elements, take all the compositions of these as well as the inverses, and that is what the subgroup is. You can show that's a subgroup, and of course, any subgroup containing G prime must contain that. So, well, I won't get into that. And the exercise over here is basically G xy G inverse is the same as Gx G inverse Gy G inverse. And that implies G prime is normal in G. And theorem is H normal in G, G mod H abelian, if and only if G prime less than equal to H. And so G mod G prime is the largest abelian quotient. So this is called the abelianization of G because it's making G abelian by taking quotients. And quotients are related to like everything. Whenever you're reducing the size of you're losing information, but quotients do like are related with minimal reduction of information, right? Because there is a G and also you're writing G prime explicitly what G prime is. So you can kind of get back G. I mean, not exactly if you're just given that this is a quotient of the group, but so it's better than subgroups. Subgroups don't give a lot of information. And this is called an abelianization of G. So another equivalent statement for solvable is it's a solvable group if and only if you look at this. G, I said G is normal, sorry, G prime is normal in G and G mod G prime is abelian. So next you can look at G prime prime, that is the derived subgroup, or okay, I forgot to give it a name. This is called the commutator subgroup or derived subgroup. Commutator subgroup because it's kind of generated by commutators, and derived subgroup term is also used because it's kind of, well, to make sense of the definition. Again, you need some more background, but well, just call it derived subgroup for now. And this is true and so on. If this sequence ends, like like this is not infinite in a sense, like after some point you stop, then you can show that they need not stop at identity. For example, as I said, for A5, as we'll see shortly, that A5, the derived subgroup is also A5. Like, that's bad. But if you stop at identity, and there are no fixed points, like if there is any fixed point, that has to be identity. That's what I'm claiming. So what am I saying? Let me continue. So if I define, say, Gn is basically Gn minus 1 prime, and G1 is, sorry, G0 is equal to G, like this. So I write this like this. So if Gi is equal to Gi plus 1, that is our sequence eventually stops. We cannot go further. Because once you have hit Gi is equal to Gi plus 1, Gi plus 2 has to be the same thing, right? because that's the same as applying it to GI. That would imply GI is equal to identity. So if you stop at identity. If this happens, that's the same as saying G is solvable. So G is solvable if and only if this happens. This sequence terminates at identity. So is the statement clear what I made? And this is much easier. Like G prime, you can construct from looking at G. You don't have to check whether a group is abelian and so on. You can just directly construct what G prime is, and you can get a sequence. So is it clear? People? Is it clear?
Yeah, the definition is fine.
Perfect. So the motivation, let's just look at one small example maybe. For abelian, it's obvious. Like if G is abelian, what is G prime? Is the subgroup generated by 1, right? Because every commutator is 1. So what is this?
Just
what is this?
the trivial group.
It
the
is
trivial group.
Exactly. What about
The
S3?
trivial group.
What about S3? This might seem hard. You have to compute so many products. But what is the equivalent characterization of this G prime? It is the largest normal subgroup, which you can use to quotient off and get an abelian group. But the only non-trivial normal subgroup inside G prime is inside S3 is A3. And S3 mod A3 is abelian. So you can show this is A3. And A3 is the same as C3. It has 3 elements. So any prime order subgroup is CP. Perfect. So what about S4? Things become harder. Try it out. Well, the first step is easy, actually. But it's not exactly very easy. So I'll leave it as an exercise. Yeah. The thing is, there is a subgroup S4 which is normal and also smaller than A4. That's the idea. So that becomes kind of complicated. Okay. So this is a way to see whether a group is solvable. So just read about generated subgroups and then you will get an idea how to proceed with this one. Perfect. So now that we have all this, we can talk about simple groups. So this process would fail, as I said, if there is a termination. What if the termination is not at E? So better if I look at G, and what if G prime is equal to G? That's the same as saying if n is normal in G, then G mod n is not abelian. So that would imply that G is not solvable. In fact, if any GI is the same as G and it's not the identity, you can just verify this fact. And sorry, not this. Sorry, n. This is true. N cannot be equal to G. Then it's abelian. But let's just look at this. G. If there are many normal subgroups, this is again hard to verify. So we again go to the coarsest possibility. That is, he has no non-trivial normal subgroup. So we say a group G is simple if n normal in G implies, see, the two trivial extremities are always normal. So n can either be the whole of G, it's normal. N can be the trivial subgroup, it's normal. But simple means that these are the only normal subgroups. There are no other normal subgroups. So let's look at a few examples to make sense. Z mod PZ, where P is a prime. There are only two subgroups. So of course there are only two normal subgroups. In fact, if G is abelian and simple, that implies G is isomorphic to CP, or Z not PZ, where P is a prime. And I am assuming again that G not equal to the trivial subgroup. That's a bad case. Now, S3 is not simple. Why is it so? Anyone? I gave an example.
A3 is the normal subgroup.
Exactly. In general, Sn is not simple because An is normal in Sn. Perfect. An has index 2 in Sn, so it is normal in Sn. But if n is greater than or equal to 5, An is simple, but the proof is hard. You can read about it, perhaps a reading exercise later on, but this is hard to prove. For A5, we can try it out, perhaps. Next. I'm so sorry. If G is abelian, if G is solvable plus simple, that implies, what should it be? Look at the composition series. If G has to be less than or equal to some H, right? Now, because G is simple and H, this is not equal because the composition series, I'm assuming it's not trivial, then H has to be equal to 1. But because it's a composition series, this is also a prime cyclic group. So if G is solvable simple, what do we get?
It's again ZPZ.
Exactly, it's a prime cyclic group. Because see, it's normal, H is normal in G, but that implies H has to be equal to 1. Because G is simple. But at the same time, because it's solvable and we are looking at a composition series, as I said, there is a composition series with abelian factors, the equivalent definition, then this is a cyclic group. Well, you're done. What else do you need? So, G is isomorphic to CP. Next, G is simple. If and only if, like again, you have to look at the definition of conjugacy classes once again. If and only if 1, Zg is equal to 1, that has to be true because Zg is normal in G. And simple plus non-abelian, sorry, I forgot to mention this. Simple plus non-abelian. If and only if, like other than these, what are the cases? These are the only simple abelian cases. Zc has to be equal to 1 because it's non-abelian. Zc cannot be there. And the other fact is, for all G belonging to G, the conjugacy class of G generates G. Because if there is a normal subgroup, which is not G and also not 1, take a G belonging to N, that would imply the conjugacy class of G also belongs to N. And that would imply the subgroup generated by this has to be a subgroup of N at least, because N is a subgroup containing G. Hence, the second condition is violated in that case, if there is a normal subgroup. Likewise, if the second condition is never violated, well, you can show the rest. I think that's an easy exercise. Like, is the statement clear what I'm saying over here? Because this has to be normal, because it's generated by conjugacy class, this has to be normal. So if it's simple, then this has to be true. This is non-trivial. Okay, well, I missed one short thing. If G minus 1, of course, because if you look at 1, then it's 1. Other than 1, if G not equal to 1, this is true. There's a statement here, this one.
Yeah.
Perfect. So if you believe me over here, and then immediately this would give you that A5 is not simple. And in fact, An for n greater than or equal to 5 is not solvable. Solvable if n is greater than or equal to 5. So now, well, composition series of a general group that might not be abelian. Like for example, A5, the composition series might not be abelian. But for A5, there is no composition series as such, because if you look at A5, and again, if you're looking at this thing, this has to be either A5, which is something which we don't want. We don't want repetitions. So if you assume this, then n has to be equal to 1. So in a composition series, like a maximal length subnormal series, it is true that any factor is abelian. So if you have a composition series, you can show that every factor is simple. Immediately you get that for any group G, you can do this. Just use induction or anything which you want to use. Because there is a composition series, there is a maximal, as I said. You can get a factorization like 1 equal to G0 is normal in G1 is normal in up to GK is equal to your G such that each Gi mod Gi minus 1 is simple. Moreover, this is true, like as we said, as we saw in Z6 and so on, the factorization, you might get it in many ways like this. There are many subnormals, but the factors are invariant. Like they are like primes. You can change the order and stuff, but it remains the same. So you can get a series. Moreover, the factors for any series, the factors remain the same. With multiplicity, the factors remain the same. Any composition series, the factor remains the same. But this requires a proof. Well, it's hard to prove it in this talk, and this is actually the famous Jordan-Holder theorem for groups. For any group, you can find a composition series with, if it's a composition series, it has to be simple. That's easy to show. But the factorization is unique. The factors are unique up to ordering, including multiplicity. Kind of like the prime factorization once again. Well, this is the famous Jordan-Holder theorem, and this is the best you can get for an arbitrary group. Well, perhaps I was thinking of, as I said, I will be covering these results about semi-direct products and exact sequences, but I think the class has been pretty long. So I think it's a good time to call it a day. So would you like to know a bit more about it? Otherwise, I think it would be better if we stop. What's your opinion?
I don't have a problem as such.
But yeah, you had classes before and now again another long talk. So perhaps it's a good time to stop. I might define what exact sequences are. And well, read about it. I'll send a note or something via the math club. So when are these two groups the same? I'm interested in knowing this. So I know there is a map phi. So when are these two groups almost identical? So always one is inside G and one is inside H. So you can project H to 1, like take everything to 1, and you can take 1 inside G as a map. What is the kernel of this map? Maybe call this map 1 and call this map 2. What is the kernel and image of this map? Ker M1. What is Ker M1? What is image of M1? This is just 1 going to 1. Nothing else. So what is the kernel?
1.
And what is the image?
1.
Yeah. And what about this one? This is projecting. Everything is going to 1. So what is the kernel?
H.
And what is the image?
1.
Exactly. Now, when is G the same as H?
When it's an isomorphism.
Exactly. When it's an isomorphism.
When I is an isomorphism.
And that's true if saying phi is an isomorphism is the same as saying kernel of phi and image of phi. What are they? Phi is an isomorphism if and only if
Yes.
kernel of phi is 1 and image of phi is H.
Can be.
So if you look at it, is this to say that this is an isomorphism is the same as saying look at every junction point or every group. Look at the map to the right and look at the map to the left. The image of the map to the left, which is inside this, is the same as the kernel of the map to the right. If this happens for a sequence like this,
It's called exact.
yeah, it's exact. And in fact, it's an isomorphism. So if this happens, phi is an isomorphism. In a much more general sense, like let phi be a random homomorphism.
Sequences.
Exactly. This is, I'll come to the definition. So this is something where such a thing happens. For a sequence of maps, if this happens, we call it to be exact. That is, suppose this is true. M1 goes to G1, M2 goes to G2, and so on. I'll be only interested in finite. This is MK. Then if at every junction point Gi, we have the kernel of M2 or Mi plus 1 basically over here, the next map is the same as the image of Mi, then we say this sequence or this chain, this is called a chain of groups. This is called to be an exact sequence. Like that's called a series and this is called a sequence in a sense. So relating to your analysis names, but this is called an exact sequence if everything is kind of the same. So we saw that a 4-element term, generally it's a convention to take the last terms to be 1 or just expand it to be 1. So this is exact if and only if phi is an isomorphism. Exact. In a much more general sense, if you look at phi to be any map from G to H, not necessarily an isomorphism. So by the first isomorphism theorem, you can study G and tell about H, right? Not H, maybe the image of phi. So you can look at G mod curve phi and you can give inference about image phi, which is inside H actually, in a different domain. So if you look at this closely and well, any subgroup is inside another group. So you look at this. The one is going to kernel of phi. The kernel of phi is again included inside G. And then G projects to image of phi, right? Using like the phi map over here, nothing else. And these are inclusions. And finally, image of phi projects to 1. So if we look at this sequence, again, what is the kernel over here? I'll just write, maybe I'll write curves and I'll write the images. So for the first map, what is the kernel?
1.
Image is again 1, as you said. And what is this one? Again, it's an inclusion. So for an inclusion, what is the kernel?
1.
It's always 1. And what is the image? It's the whole thing once again.
The kernel.
Yeah. And what is the kernel over here?
Yeah, curve phi.
What is the image? It is M phi. Like G2 image phi. Like it's basically H in a sense, but it is the image of phi. What is the kernel over here?
The last map. It's everything.
Exactly.
The
And what is
entire
the
image.
image? It's 1. Right?
Yeah.
So these are again equal. Likewise, if n is normal in G, if you look at this natural inclusion again, and G, this projects to G mod n, which projects to 1. Again, you will get a similar thing. These are inclusion, these are projection maps. There is G maps to G bar over here, and this is everything going to 1. You'll again get the same thing. So the guess is like if by first isomorphism or anything, the idea is basically you should be able to tell something about the group in the center using these two, or at least maybe not what exactly this group is, but some information is contained in these two elements about this group. So this is what is called an exact sequence in general. And well, there are something called split exact sequences. And that's also interesting to study. Perhaps when you do some topology later on, you'll make more sense of it. And I'll just end with one example. This is also true. Like take the natural inclusions once again and natural projections. This follows from the above example. So the direct product is also like in an exact sequence. So sometimes if there are 5 terms, this is called if there are 5 terms, this is called a short exact sequence. If there's an exact sequence like this, it's called a short exact sequence. In that case, we say G2 is a group extension of G1 and G3. So the exact name is, like if you look at it very closely, what exactly is happening? Or perhaps I'll use this to simplify. G1, G2, G3 is complex. So here H, we are extending it to a larger group G. We are not extending K in a sense, even though it's a quotient. Over here, we are adding elements and extending it such that it is compatible to K. So it's called an extension of H. Sorry, not I forgot which direction it is. Just give me a moment. It's an extension of H by K or an extension of K by K. Well, just look at it later on. Perhaps it would be better if I refer to my notes and do it, but I don't want to get too deep into it. So you can actually call these group extensions. Basically, you are extending, for us, it's an extension of G1 and G3 together in a sense. Like you're looking at G1 and G3 and you're patching them up to get a G2. Just like H and K, you're patching them up and getting H plus K and so on. It's called a group extension. And direct products are kind of a group extension with a nice property with respect to one of the maps. That is, if you look at, again, I draw this one maybe. If you assume this alpha has a nice property.
It has a specific kind of inverse.
Exactly. It's called a splitting property.
Then H will be like the direct sum or the direct product of H and K, and the two morphisms what is the natural inclusion and projection maps.
Exactly. That is the idea. So if you look at this, and I said it has an inverse map. One-sided inverse. It is injective, so I can expect a one-sided inverse, and there is a nice map. Then it's called a split on the left, and then it turns out that G is isomorphic to H plus K. But what if this map has a nice inverse? Yeah.
Then the existence of inverses for one of the existence of inversion of map.
Yeah.
So like the existence of beta input. Yeah.
Exactly. You're right. So the idea is very simple. If this map has an inverse, say beta from G to H, then what is happening? We call this map maybe gamma. Then you go from G to H cross K using your G is mapping to some, sorry, not alpha, beta G comma gamma G. And you have to just show that this is actually a group isomorphism, nothing else. But dually, if this happens, that this map has an inverse, this is what is called just split or right split, whatever you want to call it. Actually, this is what is called a split because this is boring, as I said. You're getting H plus K. But if this gamma has an inverse, that is, over here the inverse was like this. Over here the inverse would be something like this. Then we call this G to be a semi-direct product. And in fact, there is, as I said, a direct construction as well. Look it up in Dummett and Photo someplace else. So this is what is called a semi-direct product in a split exact sequence. So giving a split exact is the same as it's a semi-direct product. And perhaps like you have already realized that because the kernel of this is everything, this whatever map is here, for example, if I give you this exact sequence, I tell you this is exact, then you have already realized that this being exact is the same as this map has to be injective. This map has to be surjective. and the kernel of this is the same as the image of this. So I can just reduce it to looking at just one kernel image and saying that these two are injective and surjective. So the rest is simple. I guess you can just think about it later on. So I'll end the class now. It was a pretty long class, pretty long session. I'm sure that you got to learn something new about it. And this would also conclude the course, foundational course on group theory. So a few exercises, as I said, are just read about. These are some things that you should know, I guess, because I think there was a bit of a
There
problem
aren't
with
going to be
one talk.
courses on like completions and stuff like.
Completions in analysis
No,
or
like group
groups.
theory.
Okay. No,
Groups,
there won't be
groups.
anything. This is this was meant to be a foundational course with basic things. You can read up about them in many books with group after you have done some cohomology, most probably. So, or have you done filtration and stuff? That would also help, most probably. Actually,
Okay, can I ask you some questions that aren't very related to what you've talked about here for like 5 minutes? Is that okay?
Yeah, it's fine. Just give me a few minutes. I just end the class once and then I'll come back to you. Stay
Okay,
in the
thank
meeting.
you.
Okay. So subgroups generated by elements, by subsets. The next one is finitely generated abelian subgroups, abelian groups. This is an extra thing which hasn't been covered in the course, but free groups, these are also very important. These are like words, basically, nothing else. Writing words of give me an alphabet and I'll write words A, B, and I'll include the inverses of alphabets as well. Just arbitrary stuff. Some more about exact sequence and semi-direct product. The direct construction as well. It's given in Dummett and Fort or any book. Semi-direct product is present in any book. And when you will do algebra, you'll also have a look at group theory. Later on, you'll also be able to get something about it. So these are some exercises, and that would be the end of this course. Thank you so much for attending. I'll just stop sharing my screen. So thank you so much for attending. It has been, today's session specifically has been pretty long, but I hope that it was interesting and you got some nice results from it as well, and nice intuition as to what these things are. Ankon,
Yeah, that was a great lecture.
thank you so much. Venkat, if you could just stop the recording once. Okay.